Greetings of the day. I am Dr. Onika Parmar and I welcome you in this course Fundamental of Electronic Engineering. Today we are going to discuss about introduction of MOSFET. In this comprehensive introduction, we will delve into the history, types, applications and MOSFET capacitance. We will also discuss about the significance of MOSFET in the world of electronics. So, today we are going to discuss about the introduction of MOSFET, historical background of MOSFET, types of the MOSFETs, the operating mode, application of metal oxide semiconductor field effect transistors, and we will discuss the two terminal MOS structure of the field effect transistor. So, discussing about the metal oxide semiconductor field effect transistor, we also call it as MOSFET. So, M-O-S-F-E-T. M stands for metal, O for oxide and S for semiconductor, and it is a type of field effect transistor. It is a very fundamental semiconductor device that has played a vital role in shaping the landscape of modern electronics. With its ability to control the flow of electrical current in solid state circuits, the MOSFET has become a cornerstone in the digital age, enabling the creation of everything from microprocessor and memory chips to power amplifier and display drivers. The metal oxide semiconductor field effect transistor became a practical reality in 1970. The MOSFET compared to BJTs can be made very small, that is, it occupies a very small area in an integrated circuit. Since digital circuits can be designed using only MOSFET with essentially no resistors or diode required, high density VLSI circuit including the microprocessors, memories can be fabricated using the MOSFET. The MOSFET has made possible the handheld calculator, the powerful personal computer, the laptop computer which we use. MOSFET can also be used in analog circuit as well. In the MOSFET, the current is controlled by an electric field applied perpendicular to both the semiconductor surface and to the direction of current flow. The phenomena used to modulate the conductance of a semiconductor or control the current in a semiconductor by applying a electric field perpendicular to the surface is called the field effect. The basic transistor principle is that the voltage between the two terminals controls the current through the third terminal. So, let us discuss about the historical background of MOSFETs. The origin of MOSFETs can be traced back to the early 20th century when scientists began exploring the properties of the semiconductor. However, it was not until the late 1950s that significant breakthroughs were made. Mohammad Atala and Don Kang, researchers at Bell Labs, are credited with the invention of MOSFET in 1959. This discovery marked a turning point in semiconductor technology and laid the groundwork of a new era of electronics. So, discussing about the types of MOSFET or moving towards the type of MOSFETs, there are primarily two types of MOSFET. So, the first one is N-channel MOSFET. In this type, a positive voltage is applied to the gate terminal, creates an electric field that enhances the flow of electron in the semiconductor channel, allowing current to pass from the source to the drain. P-channel MOSFETs. The second one is P-channel MOSFET. So, in a P-channel MOSFET, a negative voltage at the gate terminal enhances the flow of holes in the channel, permitting current to pass from drain to the source. So, basically there are two types of MOSFET. One is a N-channel MOSFET and second is a P-channel MOSFET. It is also known as NMOS and PMOS. Now, moving towards the operating mode of the MOSFETs. The MOSFETs can operate in various modes depending upon their construction and the applied voltage. So, the first one is enhancement mode. These MOSFETs are normally off and require a specific voltage at the gate terminal to turn them on, allowing the current to flow between the source and drain. The depletion mode MOSFETs are normally on and they requires a voltage at the gate terminal to turn them off, thereby blocking the flow of current. So, basically there are two modes of operation, one is the enhancement mode and second is the depletion mode. So, while fabricating this MOSFETs, we decide if the MOSFET will be of enhancement type or the depletion type. In a depletion type MOSFET, the channel is already present, it is fabricated during the production, while in a enhancement mode MOSFET, channel is not present and a certain gate voltage is required to turn on the MOSFET. Moving forward towards the application of MOSFETs. The versatility of MOSFET is reflected in their wide range of applications. First is digital electronics. MOSFETs are the basic building block of digital logic gates and integrated circuits. They are vital in the creation of microprocessor, memory chips, digital signal processing unit, digital processors. All these are made with the MOSFETs. They are used in amplification. In analog circuits, MOSFET serves as amplifier in audio system, amplifying weak signal for a clear sound. They are widely used as switches as well. So, due to their high switching speed and efficiency, MOSFETs are used in power supplies, voltage regulators and high frequency switching circuits. They are used in memory devices as well. Flash memory widely used in USB drivers, SSDs and memory card relies on MOSFET for data storage. MOSFET has application in display units as well. MOSFETs control the pixels in LCD and OLED's display, enabling vibrant screen for modern televisions, smartphones and monitors. So, moving forward towards two-terminal MOS structure. The heart of the MOSFET is the metal oxide semiconductor capacitor shown in this figure. As I have told you, MOS, this stands for metal oxide semiconductor. So, here in this figure we can clearly identify there are three layers. So, the first one is the metal, second one is the insulator, and the third one is semiconductor. So, it forms the layer of metal, oxide and semiconductor. The insulator is basically made of silicon dioxide. Now, in the research phases, there are various other oxides which are also used, or other insulators which are also used, but in the basic structure a silicon dioxide layer is grown on the silicon surface. So, the three layers are metal, insulator and the semiconductor. So, the thickness of the oxide is represented as Tox, and this oxide acts as a gap between the direct contact of the metal and the semiconductor. Hence, there is no electrical contact between the metal and the semiconductor. They are separated by the oxide. So, this oxide thickness is generally represented as Tox, and we can see there is a plate of metal and then an insulator, then again there is a semiconductor. So, we can observe there are two plates with a dielectric layer or a insulating layer between them. This replicates to a capacitor structure, if you remember. So, in the capacitor what is there? There are two metal plates with a dielectric layer in between them. Here the dielectric is replaced by the semiconductor insulator, and the two metal plates are the metal and the semiconductor layer. So, this forms the basic MOS capacitor structure. This is highly important in discussing MOSFETs. The metal may be of aluminum or some other type of metal. In most of the cases, the metal is replaced by a high conductivity polysilicon layer deposited on the silicon dioxide. However, the term metal is usually still used in referring MOSFETs. In the figure, the parameter Tox is the thickness of the oxide and epsilon ox is the oxide permittivity. The physics of MOS structure can be explained with the aid of a simple parallel plate capacitor. The capacitance of a parallel plate capacitor, neglecting the fringing fields, is C is equals to A by D, where A is the area of one plate, D is the distance between the plates, and epsilon is the permittivity of the medium between the plate. So, C is equals to epsilon A by D. So, figure 2 shows a parallel plate capacitor with the top plate at a negative voltage with respect to the bottom plate. An insulator metal separates the two plates. So, here we can see there are two plates and the plates are provided with the potential, and the top layer has negative potential applied on it, and they are placed in a distance d, and the permittivity between them is epsilon, and their electric field is generated in the direction from positive to negative. So, this shows a parallel plate capacitor with the electric potential applied, showing the electric field and the conducting charges. With this bias, a negative charge exists on the top plate and a positive charge exists on the bottom plate. An electric field is induced between the plate as shown in the figure. A MOS capacitor with p-type semiconductor substrate is shown in figure 2b. The top metal terminal, also called as the gate, is at negative voltage with respect to the semiconductor substrate. So, this figure shows a p-type MOS with p-type substrate layer, and the gate is of metal. It can be of polysilicon as well. Okay. So, the gate is of metal and it replicates with the previous figure. So, a corresponding MOS capacitor with negative gate bias shows the electric field and the charge flow. So, the electric field moves from positive to the negative side. From the example of the parallel plate capacitor, we can see that a negative charge will exist on the top metal plate and an electric field will be induced in the direction shown in the figure. If the electric field penetrates the semiconductor, the holes in the p-type semiconductor will experience a force towards the oxide semiconductor interface. The equilibrium distribution of charge in a MOS capacitor with this particular applied voltage is shown in figure 2c. So, here we can see the MOS capacitor with an accumulation layer of holes. So, the semiconductor which we are using here is a p-type semiconductor. In this p-type semiconductor, the majority carriers are holes. So, when we apply a negative potential at the gate terminal or to the metal, the positive charges will align at the surface of contact between the oxide and the semiconductor. So, the positive charges, that are the holes, will be attracted by this negative potential and they will get accumulated due to this attraction force. They will move upward and they will get accumulated at the oxide and semiconductor interface, as the oxide is restricting them to flow from the semiconductor to the metal. Hence, they will be accumulated there, and the region formed here is called the accumulation region. The region of the extra holes or the positive charges accumulated beneath the oxide is known as the accumulation layer of the holes. An accumulation layer of positive charged holes at the oxide semiconductor interface corresponds to positive charge on the bottom plate of the MOS capacitor. MOS capacitor with a p-type substrate shows the same MOS capacitor, but with the polarity applied of the voltage is reverse. Now, a positive charge exists on the top of the metal plate and the induced electric field is in the opposite direction as shown in figure 3a. So, here there is a p-type semiconductor. In a p-type semiconductor, the majority carriers are holes. Now, we have changed the biasing. We are applying positive value at the metal interface and negative value to the semiconductor. Now, these holes will be pushed downwards because similar charge repels to each other. Now, there is a positive charge at the metal interface. So, they will repel the holes and the hole will come in the downward direction. They will be attracted by the negative potential applied to the semiconductor. So, they will be attracted downwards, and there is a electric field that will be existing from positive to negative terminal. So, this is the effect of a positive gate bias, showing the electric field and charge flow in MOS capacitor with a p-type substrate. So, in this case, if electric field penetrates the semiconductor, holes in the p material will experience a force away from the oxide semiconductor interface. As the holes are pushed away from the interface, a negative surface charge region is created. Because of the fixed capacitor, because of the fixed acceptor impurity atoms, the negative charge in the induced depletion region corresponds to a negative charge on the bottom plate of the MOS capacitor. So, figure 3b shows the equilibrium distribution of charge in a MOS capacitor with this applied voltage. So, here we can see that there is a positive potential applied to the metal and negative potential is applied at the semiconductor. So, the MOS capacitor with induced space charge is shown here. So, what will happen? There will be the induced negative charges at the semiconductor and oxide interface. The holes will be attracted towards the negative potential, and the negative charges or the electrons will be attracted towards the positive potential, and they will accumulate beneath the semiconductor and oxide interface. They will accumulate beneath the oxide layer, and there will be a space charge region formed. This is induced negative space charge region. The width of this induced negative space charge region is x dt. So, when a large positive voltage is applied to the gate, the magnitude of the induced electric field increases. Minority carriers electrons are attracted to the oxide semiconductor interface as shown in the figure. So, here we can see that there is a positive potential applied at the metal and negative potential is applied at the semiconductor. So, the semiconductor is of p type. The holes will be attracted towards the negative potential and the electrons will move towards the positive potential, and there will be a region developed. This is known as induced negative space charge region. Actually, it forms the inversion layer. So, there is a accumulation of negative charges. So, this region is called electron inversion region. This region of minority carrier electron is called as electron inversion region. The magnitude of charges in the inversion layer is a function of the applied gate voltage. MOS capacitor with n-type substrate. The same basic charge distribution can be obtained in a MOS capacitor with a n-type semiconductor substrate. Figure 4a shows the MOS capacitance structure with a positive potential applied at the top of the gate terminal. So, here we can see that the metal is provided with the positive potential and the semiconductor is provided with the negative potential. This negative potential at the semiconductor layer will repel the electrons away, and the positive potential at the metal interface will attract the electrons in the semiconductor. Hence, a layer of charges will be formed beneath the oxide interface. So, this layer of negative charges beneath the oxide interface is called as the accumulation layer. A positive charge is applied on the top of the gate and electric field is induced in the direction shown. In this situation, an accumulation layer of electron is induced in a n-type semiconductor. Figure 4b shows the case when a negative voltage is applied to the gate terminal. A positive space charge region is induced in the n-type substrate by the induced electric field. Here in the figure we can see that there is a induced positive space charge region due to the polarity of the potential applied at the metal and the semiconductor contacts. So, when a large negative voltage is applied, a region of positive charge is created at the oxide semiconductor interface as shown in figure 4c. This region of minority carrier holes is called a hole inversion layer. The magnitude of the positive charge in the inversion layer is a function of the applied gate voltage. So, this figure shows a MOS capacitor with a induced surface charge region and hole inversion layer due to large negative gate bias. So, the holes will be accumulated beneath the oxide interface and a hole inversion layer will be formed here. So, the term enhancement mode means that a voltage must be applied to the gate to create an inversion layer. For the MOS capacitor with p-type substrate, a positive gate voltage must be applied to create the electron inversion layer. For the MOS capacitor with a n-type substrate, a negative gate voltage is applied to create hole inversion layer. So, in the case of the enhancement mode, we have observed that we required a potential to have an inversion layer or formation of channel from the source to the drain. So, in the case of enhancement mode MOSFETs, we does not have a layer of charge present in the device. We have to create it with the help of the applied biasing. So, in the enhancement type MOSFET, no channel is present in the device and it is formed with the external potential applied to the device. Either is the case of a p-type MOSFET or in the case of a n-type MOSFET. This is the end for today's lecture. In this lecture, we have discussed upon the introduction of MOSFET. We have seen the background or the historical background of the MOSFET. We have discussed the types of MOSFETs and their operating modes. We have discussed upon the application of MOSFET and we have also discussed about the two-terminal MOS structure. The two-terminal MOS structure is a very significant structure in the case for the further discussion of MOSFET. So, thank you for your patience listening. Hope to see you in the next lecture.